right here that I can solve using separation of variables. Third part will be to solve the IBVP, okay, using separation of variables, okay? And then I can tell you this, add V to U bar to get U, okay? All right, so this is common in the separation of variables problems when you have inhomogeneities arise, okay? So what is separation of variables tell us to do? Well, we start off by assuming that the constituent functions of V are, I'll call them big X and big T, okay? So essentially, for our homogeneous problem, okay? In the case of inhomogeneous problems, we always start, just like you did in like linear ODEs, by solving the homogeneous problem where I take that to be 0. Then you can essentially build the inhomogeneous solution from the solutions to the homogeneous problem, as I'll show. Okay, so for the homogeneous problem, right? Remember, Vt equals Vxx. We can go through this again just to be clear about it. I get x t prime, x prime prime t. If I rearrange things right, I get t prime over t is equal to x prime prime over x. And I'm going to set this equal to lambda, okay? So just for in the x case, I get that x prime prime plus lambda x is equal to 0, okay? And then for my BCs, what do I get? I just look up here, right? And I have that, well, this is equal to x0 t of t. This is equal to x of pi t of t. So this thing must be 0, and this thing must be 0 in order for that part to not be just trivial. So I get x of 0 equals x of pi equals 0. So this is my good old Sturm-Liouville problem, you know, or my boundary value problem, or my eigenvalue problem, whatever you want to call it, okay? We've solved this before. What are the solutions to this? To get this on a prelim, you should be doing backflips because it's probably the easiest of these such problems to solve. It's sines, right?
Sine, yeah.
Yeah. All right. So we just have sines, right, to deal with. It's not bad. So x of x is equal to sine of nx. Okay. We can go through that whole process, but yeah, we've solved that problem before. So I'll just jump to the solution, right? And I'll get to the sticky parts that are maybe new to this problem. Okay. So the formal solution, to remember, we're still just solving the homogeneous problem, okay, is v of xt equals the sum from n equals 1 up to infinity, tn of t sine of nx. I still haven't done anything with the time-dependent problem, and you say I haven't dealt with the issue of the inhomogeneity. Well, now we're going to, okay? So if I take this and I say, well, my solution's going to look like this, but I still don't know what these are, I'm going to use those to build in the inhomogeneity. So in that case, I get the sum from n equals 1 up to infinity. I can pass this operator through into this this solution that I've derived, and I get tn prime plus n squared tn multiplied by sine of nx is equal to e to the minus t sine of 3x, right? So this came from here, and this came from here, right? I just differentiated my sine twice, okay? If I'd had sines and cosines, right, I would have had to expand this out into, sines and cosines. If I'd had different numbers of derivatives in there or whatever. But it works out nicely so that I just have this now it's kind of a differential operator acting on t that's my coefficient for my eigenfunctions, right? Temporal coefficients that need to account now for this. So how do I deal with this? Well, it turns out what I have is actually an infinite number of differential equations in disguise here, right? Sort of wrapped up in here. I can exploit the orthogonality of the eigenfunctions. This is why orthogonality of the eigenfunctions is so important, because otherwise you could not pull this mess apart, right? But because sine and x are orthogonal in the L2 inner product, I'm good, right? So essentially, if I take the L2 inner product with sine mx, and then after that, I'm going to change m back to n. What I would get is, and you can just kind of read it off here, right? Tn prime of t plus n squared Tn of t, right? This coefficient is equal to this, right? And you say, well, how does this right-hand side affect things? It's only going to affect a single term, the sine 3x term. Because if I take the inner product of this with sine of mx, right, I'm only going to get a non-zero term on the right-hand side when m is equal to 3, right? And otherwise, it's going to be 0. So I get this sort of set of differential equations that are homogeneous when n is not equal to 3, and inhomogeneous when n is equal to 3, okay? Questions about this? You're almost home free at this point because then you're just back to solving ODEs, okay?
Do we not have a factor of 2 over pi or something from the integral of sine nx and sine nx?
No, because that factor would be common everywhere, so you could just cancel it out, and I think you can essentially cancel it out, right? Because it should show up everywhere.
Right. Thank you. Sorry.
Yeah. No, that's fine. Yeah. Other questions? Okay. All right. I think I can finish this off in 12 minutes. Okay. All right. So moreover, we have a differential equation, but we like an initial condition, right? We need that. So at t equals 0, note that v of x0 is equal to 1 minus x over pi. And then remember, everything has to be filtered through these eigenfunctions, right? So I got to get the eigenfunction part of all of these things, right? So that is how I get my initial conditions, is to say, well, my initial condition in V is going to be an expansion in my eigenfunctions, okay? It's not hard to peel these off. Again, you just use the orthogonality of sine of nx, right? Okay, so this implies that Tn of 0, right? And this is, I think, what Caleb was asking about. You have 2 over pi integral from 0 to pi, 1 minus x over pi sine of nx dx is equal to what? You can carry out the integration by parts and everything, and you get 2 over n pi, okay? Now, I remember I had to use odd extension here in order to justify this integral, right? Because that's how they would be L2 inner product orthogonal to each other, right? And then I essentially used an odd extension also of the initial condition in order to do that. Okay, so Tn of 0 is just equal to 2 over n pi. Okay, so then therefore at n is not equal to 3, what do I have? Let's just go through that case, right? Tn prime is equal to minus n squared Tn, along with this initial condition, right? So I also have Tn of 0 is equal to 2 over n pi. And if I take all this together, right, this is just going to be an exponential function, like you'd expect. And then this is going to be parked out front. So you have Tn of t is equal to 2 over n pi e to the minus n squared t. Okay? So this n squared t, right, that's good news as far as, you know, killing off all the high frequency modes as you'd expect that you would get from the heat equation. Okay? So now the last bit of work is just with that inhomogeneous problem, right? So if we go now to n equals 3 case, okay, then how do we get that? Well, we have T3 prime plus 3 T3 is equal to the right-hand side now, e to the minus t. Okay. Well, we know the
9T3.
Sorry.
It's n squared.
Oh,
Should be
sorry,
nine.
sorry. It should be 9. Yeah, you're right.
Yeah.
You're right. 3 squared. Thank you. Right. Okay. So now what do we got? So this has a homogeneous solution, right? Which is just going to be T3 equals, you know, some a e to the minus 9t. And then our particular solution would be b e to the minus t. So you could use integrating factors, you could use method of undetermined coefficients. We can use method of undetermined coefficients, okay? So if we use undetermined coefficients here, right? Just on the particular solution, because we know that the linear operator is just going to kill the homogeneous solution. Then we have that T3 prime plus 9T3 for the b equals e to the minus t is going to be equal to minus b e to the minus t plus 9b e to the minus t. And we know that this is supposed to equal e to the minus t, right? So we get 8b e to the minus t equals e to the minus t. So b is an 8. Okay. All right. So at the end of the day, right? So since T3 of 0 is equal to 2 over 3 pi, remember that's just our initial condition for everything. This is our n in this case. Then we have this is equal to a plus 1 over 8, right? Because T3 of t is equal to a e to the minus 9t plus 1/8 e to the minus t, okay? So we can solve this for a, and we get a is equal to 2 over 3 pi minus an eighth, okay? So finally, we get T3, sorry, I know I'm being a bit sloppy here, 2 over 3 pi e to the minus 9t plus an eighth e to the minus t e to the minus 9t. okay? So we're pretty much done. We just have to put everything back together, right? So what did we learn here? Essentially, what pops out of having a forcing term is that you get an inhomogeneity in your temporal coefficients, okay, that then requires you to introduce, particular solutions for a subset, or it could potentially be all of your differential equations, right? So let me just wrap this up and then I'll kind of recap, right? So all together now, I have that v of xt is equal to, well, I know it's just this infinite sum, Tn of t sine of nx is equal to what? Well, I have a special term out in front here, e to the minus t minus e to the minus 9t over 8 sine of 3x, right? And then this term here, right, is like just what happens with all of the other terms. So I have a 2 over pi here out front, sum from n equals 1 up to infinity, e to the minus n squared t over n sine of nx there. Sorry to smoosh that a bit, okay? And you may be worried, oh, what if, no, you wouldn't be worried about anything. Everything's fine here, right? Because essentially these coefficients are decaying nice and fast, okay? And then this thing here, well, with time it's going to decay, but it's just, it's just one Fourier mode, okay? So u of xt is equal to then, well, remember now I have to add on u bar plus v. So I get x over pi plus e to the minus t minus e to the minus 9t over 8 sine of 3x plus 2 over pi sum from n equals 1 up to infinity e to the minus n squared t over n sine of nx. Okay. So what did we learn here? Okay. First of all, remember that when you're solving a forced PDE, you just solve for the homogeneous solution first, and then you use the temporal coefficients in order to construct the contribution of the inhomogeneity. That'll just pass through in as inhomogeneities in your temporal differential equations that you get. But the eigenfunctions that you build can be the ones from the homogeneous problem. If you have inhomogeneous boundary conditions, sometimes you can handle that by looking at the steady state solution, at least in the case of Dirichlet boundary conditions. Although sometimes, again, you have to sort of, build these things in as we did in the, I think the other forced heat equation problem I did in lecture, okay? And then once you've subtracted off some of these inhomogeneities, you have to remember to add them back in by adding in the solution that you got from the steady state problem, or whatever the thing was that you subtracted off. So if you want more examples of this, there's past prelim problems that go through kind of related cases. So this is really where separation of variables, you have to throw on a few different bells and whistles, but hopefully this gives you a sense of what to do in those situations. So questions about this before we conclude? Or we're just wrapping up at 12 today. Okay.
I have one question that's kind of unrelated.